There's a stream of antimatter hitting Earth right now. Tiny particles called positrons are arriving in far greater numbers than expected, and for years no one could explain where they were coming from. At first, the data looked so strange that many scientists thought we might finally be seeing signs of dark matter. But the real source turned out to be something else. A star that exploded hundreds of thousands of years ago, leaving behind a rapidly spinning core unlike almost any other we've studied. That remnant is called Geminga, and it has become one of the most important pulsars in the galaxy for understanding antimatter. When Geminga was first noticed in the early 1970s, it wasn't through a telescope aimed at stars, but through an instrument designed to catch high-energy radiation. NASA's Small Astronomy Satellite, known as SAS-2, detected an unusual glow of gamma rays coming from the direction of the Gemini constellation. At the time, gamma rays were mysterious in their own right. Unlike visible light, which passes through space in straight beams we can trace back to stars, gamma rays are extremely energetic photons produced in the most violent places in the universe: supernova explosions, black holes, and the remnants of dead stars. The strange thing about this source in Gemini was that it didn't match any known object. Astronomers gave it a placeholder name, Geminga, coined by Italian physicist Giovanni Bignami. It was a clever mix of Gemini and gamma, but in Bignami's Milanese dialect the word also meant "it's not there." And that double meaning stuck. Geminga was something that produced radiation we could measure. But when telescopes looked in its direction, there was nothing obvious to see. It was a glow without a clear origin. And that contradiction kept it at the edge of astronomy for years. The puzzle deepened over the next decade. In 1983, using the Einstein X-ray satellite, Bignami's team detected a faint signal in X-rays from the same patch of sky. That was the first real hint that Geminga wasn't just a cloud of gamma rays floating through the Milky Way, but a compact object emitting across more than one type of radiation. Even so, the evidence was thin. Astronomers could narrow the search area, but they still couldn't say what Geminga actually was. It became one of those frustrating cases in astrophysics where you have signals, numbers, and graphs, but no clear picture of the source. The breakthrough came in the early 1990s. Two separate satellites, ROSAT, an X-ray observatory, and EGRET, a gamma-ray telescope on NASA's Compton Gamma Ray Observatory, detected pulses coming from Geminga. The signals weren't constant. They came in bursts, repeating at a precise rhythm. A flash every 0.237 seconds. That was the smoking gun. Only one type of object was known to produce radiation in such pulses, a neutron star spinning at incredible speed, with beams of radiation sweeping across space like a lighthouse. Geminga had finally revealed itself as a pulsar, but not an ordinary one. Most pulsars discovered before then were first found through their radio waves, their steady beacons picked up by radio telescopes. Geminga, on the other hand, appeared to be silent in radio. It was blasting out gamma rays and some X-rays, but radio observatories heard nothing. That silence made it the first known radio-quiet pulsar, a category that didn't even exist before Geminga. It also explained why the object had gone unnoticed for so long. Our instruments were tuned to the wrong frequency. By the time Geminga's identity was pinned down, astronomers realized it was the third gamma-ray pulsar ever discovered, after the famous Crab and Vela pulsars. Yet it didn't resemble either of them closely. Unlike Crab and Vela, Geminga didn't seem to sit inside a glowing nebula from its parent supernova explosion. It looked bare, isolated, almost stripped of the usual signs left behind when a star dies. That odd absence of a nebula, combined with its lack of radio emissions, gave Geminga a reputation as the misfit of the pulsar family. And if that wasn't strange enough, follow-up observations showed Geminga wasn't just sitting still in the sky. Comparing data from telescopes in Europe and Hawaii, astronomers noticed it had shifted position slightly over time. Geminga was on the move, streaking across the galaxy at over 200 kilometers per second. For an object so small, just 20 kilometers across, but weighing more than our Sun, that kind of speed was staggering. It meant Geminga was not only unusual in how it shone, but in how it traveled. A compact corpse of a massive star, hurtling through interstellar space faster than most stars ever move. By the mid-1990s, Geminga had transformed from a nameless gamma-ray haze to one of the most studied pulsars in the Milky Way. Yet the biggest question still hadn't been answered. Why was this strange object connected to the antimatter raining down on Earth? That connection would take another 2 decades to piece together. Most stars only drift by thousandths of an arcsecond per year. Geminga was covering 0.2 arcseconds annually, making it one of the fastest known neutron stars. This speed is a direct consequence of its birth. When the massive star that created Geminga exploded about 340,000 years ago, the supernova wasn't perfectly symmetrical. That imbalance kicked the remaining core forward like a cosmic cannonball. Then there are the trails. As Geminga cuts through the interstellar medium, it leaves behind 2 long, faint tails of X-rays, each stretching trillions of kilometers into space. These trails were revealed in the early 2000s with ESA's XMM Newton telescope and confirmed by later observations. They look like the wake of a boat cutting through water, but instead of foam and waves, they are streams of high-energy particles accelerated by the pulsar's rotation and magnetic field. That alone sets Geminga apart. Few pulsars show such extended, comet-like features in X-rays. Another reason Geminga stands out is its energy output. Nearly all of its radiation, around 99%, is in the gamma-ray range. That makes it one of the brightest gamma-ray sources in the Milky Way. To put this into perspective, if you had gamma-ray vision instead of eyes sensitive to visible light, Geminga would dominate your view of the sky. It is effectively a compact particle accelerator, generating radiation thousands of times more energetic than anything produced on Earth. Taken together, its quietness in radio, its absence of a visible nebula, its extraordinary velocity, and its dominance in gamma rays, Geminga isn't just another neutron star. It's a one-off example that pushed astronomers to rethink how pulsars behave. And, as later research showed, those unique features are directly tied to why Geminga plays such an important role in the antimatter puzzle. The real turning point in Geminga's story came when scientists began to connect it to something much larger: the unexplained excess of antimatter near Earth. Antimatter isn't science fiction. It's a real physical counterpart to normal matter. And in this case, we're talking about positrons, which are simply electrons with a positive charge. In theory, positrons can be produced by a variety of cosmic events: radioactive decay, supernova remnants, and interactions between cosmic rays and interstellar gas. But the number of positrons reaching Earth was far higher than these processes could explain. The Alpha Magnetic Spectrometer, AMS-02, mounted on the International Space Station, made this clear in 2011. It was built to detect cosmic rays, antimatter, and possibly even evidence of dark matter. Within its first years of operation, AMS-02 recorded hundreds of thousands of positrons, a sample so large it dwarfed all previous measurements combined. What stood out was not just the amount, but the energy distribution. At higher energies, the number of positrons didn't drop off the way models predicted. Instead, it leveled off, suggesting a powerful source was pumping them into space close enough to Earth for us to detect. For a time, dark matter was the favored explanation. If dark matter particles were colliding and annihilating each other, they could produce positrons. Many physicists hoped the AMS-02 data was the first indirect clue about the nature of dark matter, something scientists have been chasing for decades. But the pattern didn't quite fit. The observed flux of positrons looked more like it was coming from astrophysical accelerators than from exotic new physics. That's when pulsars, and especially Geminga, became the leading suspects. Pulsars are natural particle accelerators. Their magnetic fields are staggeringly powerful, and their rotation can fling charged particles, electrons and positrons, to nearly the speed of light. In Geminga's case, Its gamma-ray dominance hinted that it was accelerating huge amounts of particles, creating a cloud of electrons and positrons around it. In 2017, the High-Altitude Water Cherenkov (HHWC) observatory provided direct evidence of this. HWC detected a giant halo of gamma radiation surrounding Geminga, extending dozens of light-years across. That gamma-ray glow is thought to be produced when electrons and positrons scatter off starlight, boosting it into the gamma-ray range. This halo was critical because it showed Geminga wasn't just creating high-energy particles, it was trapping them in a vast region of space. Over time, some of those particles leak out, diffuse through the interstellar medium, and eventually reach Earth. Modeling based on the size and intensity of Geminga's halo suggested that this single pulsar could be responsible for as much as 20% of the excess positrons detected here. That alone was enough to shift the consensus away from dark matter as the main explanation. Add in contributions from other nearby pulsars, and the mystery of the positron excess looked increasingly like an astrophysical problem, not an exotic physics breakthrough. Geminga, the once misunderstood gamma-ray haze, had become central to solving one of the most pressing questions in cosmic ray physics. It wasn't proof of dark matter, but it was proof of how much we had underestimated pulsars as sources of high-energy particles. And while this explanation may have disappointed those hoping for a direct window into new physics, it opened another. Pulsars like Geminga aren't just dead stars. They're active, ongoing engines reshaping the particle environment of our galaxy. Even though Geminga solved part of the antimatter mystery, it hasn't stopped raising new questions. In fact, the last few years have given us some of the most important updates about what's happening around this pulsar, and the picture isn't as simple as it first appeared. One of the first surprises came from looking for Geminga's X-ray halo. If Geminga is constantly accelerating electrons and positrons, those particles should spiral around magnetic field lines and emit X-ray synchrotron radiation. Astronomers expected to see a faint but extended glow in X-rays around the pulsar. Using observatories like XMM Newton and NuSTAR, they searched for it in detail. But nothing turned up. No diffuse X-ray halo was found. Instead of being a dead end, this absence provided a new clue. It meant the magnetic field near Geminga is weaker than expected. All the conditions for synchrotron emission aren't right. That gave astronomers stricter limits on the environment, forcing them to rethink how particles actually diffuse away from the pulsar. The second development was refining the size of the slow diffusion zone. When HWC first mapped Geminga's gamma-ray halo, it became clear that particles leaving the pulsar weren't spreading through space the way standard models predicted. Normally, cosmic rays scatter through the interstellar medium fairly quickly. But around Geminga, they were moving sluggishly, stuck in a bubble of turbulence. New analysis has narrowed that bubble to about 30 to 70 parsecs across. That's tens of light years. But on galactic scales, it's still a confined zone. This matters because it decides how many of the positrons can escape and travel far enough to reach Earth. Then there's the shape of the halo itself. Recent studies suggest it isn't perfectly symmetric. Instead, there are hints of asymmetry in the gamma-ray glow, with some regions brighter than others. That suggests the environment around Geminga isn't uniform. Magnetic fields, local gas density, or turbulence could all be distorting how particles move, making some pathways easier for positrons to escape than others. If true, that means the positrons we detect on Earth don't just depend on how Geminga produces them, but also on how the surrounding space channels them. Another unresolved issue is the energy dependence of the halo. At very high energies, in the tera-electron-volt range, Geminga glows brightly, and the halo is obvious. But in the lower energy giga-electron-volt range, the halo seems to vanish. The Fermi telescope, which is sensitive to giga-electron-volt gamma rays, has struggled to find the same kind of extended emission. This gap is puzzling. It suggests that either lower energy particles are diffusing in a way that spreads them too thin to detect, or they're being absorbed or cooled before producing gamma rays we can see. Either way, it points to a process we don't fully understand yet. Taken together, these updates show that Geminga isn't just a solved mystery. It's now a testbed for studying how cosmic rays behave, how magnetic turbulence works, and how particles move through the galaxy. What started as a strange gamma-ray haze has turned into one of the most important laboratories for high-energy astrophysics. Scientists may have ruled out dark matter as the explanation for the positron excess, but the details of how pulsars like Geminga accelerate and release particles are still being pieced together. And with every new observation, Geminga keeps forcing revisions to the models. When the alpha magnetic spectrometer first showed the unexpected rise in positrons, many physicists hoped it was the first concrete signal of dark matter. The idea was simple. If dark matter particles collide and annihilate, they could produce positrons as a byproduct. That explanation was attractive because it gave us a way to connect a direct observation with one of the biggest mysteries in physics. For several years, this was the dominant theory. But as more data came in, the case for dark matter weakened. The positron signal didn't have the sharp cutoff or the spectral shape expected from dark matter annihilation. Instead, it looked more like something produced by astrophysical accelerators. The discovery of Geminga's massive gamma-ray halo and its ability to explain up to a fifth of the positron excess on its own was the turning point. Combine that with other pulsars of similar age and distance, and the excess could be accounted for without invoking dark matter at all. This doesn't mean dark matter isn't real. It simply means the positron puzzle is no longer considered strong evidence for it. Researchers still pursue other ways to detect dark matter, through underground detectors searching for rare interactions, through gravitational effects on galaxies, and through cosmological studies of the early universe. The antimatter data, once a leading candidate for indirect detection, is now better explained by pulsars like Geminga. Recent studies, including a February 2025 analysis of pulsar catalogs, suggest that nearby pulsars like Geminga and monogem could dominate up to 70% of the galactic positron flux observed by AMS-02, solidifying this astrophysical origin and further sidelining dark matter interpretations. What's important here is the shift in perspective. Rather than being a disappointment, this result highlights how much we still have to learn from familiar astrophysical objects. Geminga has become a natural laboratory for testing theories of particle acceleration and cosmic ray transport. By studying its halo, its unusual radio silence, and its asymmetric diffusion zone, scientists are refining models that apply to cosmic rays across the galaxy. For dark matter research, the lesson is that the search must continue elsewhere. The positron anomaly no longer points in that direction. But for astrophysics, the lesson is that pulsars can shape their surroundings in far more complex ways than we once thought. A single neutron star, only a few dozen kilometers across, can influence the particle environment of the Milky Way and even affect the measurements we make here on Earth. Geminga started out as a mystery source, named as if it were not there. Today, it is one of the clearest examples of how a single object can transform our understanding of cosmic antimatter. It may not have given us dark matter, but it has given us something equally valuable, a clearer view of how the universe really works. Looking back, Geminga's story shows how science often advances. What started as a vague gamma-ray haze in the 1970s turned into one of the most important case studies in high-energy astrophysics. For decades, it was a source without an identity, a signal without a clear explanation. Only with the arrival of better instruments, X-ray satellites, gamma-ray telescopes, and eventually detectors on the International Space Station, did the pieces start to fall into place. Geminga proved to be a pulsar, but not the kind astronomers expected. It was almost silent in radio waves, lacked an obvious supernova remnant, and moved across the galaxy at extraordinary speed. Later, it revealed giant X-ray trails and a gamma-ray halo so vast it could explain much of the antimatter reigning on Earth. Each step of the investigation forced scientists to adjust their assumptions about what pulsars can do. More than that, Geminga demonstrates the surprising interconnectedness of cosmic phenomena. What once looked like an abstract puzzle about invisible matter has instead become a story about the afterlife of stars, the dynamics of extreme magnetic fields, and the way energy moves through the galaxy. By chasing dark matter, we stumbled upon a deeper understanding of pulsars, objects that, far from being silent remnants, are active sculptors of the interstellar medium and crucial players in the grand cosmic ecosystem. It is a humbling example of how the cosmos often redirects our questions, providing answers in places we did not initially think to look. The implications reached beyond pulsar physics. For a time, the positron excess was seen as one of the most promising signs of dark matter. The discovery that pulsars like Geminga could explain it redirected the search. Instead of solving dark matter, the puzzle highlighted how incomplete our models of cosmic ray production and propagation still are. What looked like evidence for new physics turned out to be a reminder that the known universe still holds surprises we haven't accounted for. Today, Geminga is more than just an object of curiosity. It is a working laboratory. By studying its halo, its particle environment, and its asymmetric diffusion zone, scientists can refine the very models that describe how high-energy particles move through the Milky Way. That knowledge doesn't just help explain Geminga, it also improves our understanding of cosmic rays, interstellar magnetic fields, and the conditions that shape our galaxy. Geminga's name means it is not there, but it is very much here in the data. From a hidden gamma-ray glow to a cornerstone of cosmic ray research, it has reshaped our view of antimatter in space. The puzzle of the positron excess may not have led us to dark matter, but it showed us that even the most familiar objects, dead stars, can still surprise us in ways that change the direction of science.